What's up everybody, welcome to another Python 3 recipe, and today's video is named Being Clever on Sorted Sequences. And here we have two problem statements, and the first one is, let's say we are still building our movies reviews website and we have a couple of reviews for each movie, and we are trying to maintain the list of these reviews in a sorted order, with the worst at the beginning and the best review at the end. And every now and then we want to search for some reviews on that list and see if a given score has been assigned to that movie, to a particular movie. In order to do that, let's say we are trying to search for 3.1 in this review list. One way we can do it is just iterate over the list and here and go there and there and there and there up till the end and say no, we haven't found it. And another way, same thing for 1.5, we can iterate 0 and then 1.5, yes, that's a hit. But such search is a linear search in a way that, in the sense that in order to find if the information is if a given score is in the list, you have to iterate over all the elements in the list, which is linear. As this diagram shows here, the time complexity grows linearly with the length of the list you're searching in. But given the fact that the list is sorted, the list of reviews is sorted, can we do better? That's the purpose, that's the problem statement here. Can we do better? And the answer is definitely yes, definitely, and we will see how. But before that, let's first look at the very wrong implementation we just discussed, and by running this code snippet, which implements a linear search in Python. And like we said, if we want to search if a new review is within the sorted review, we just iterate over all the reviews in the sorted review, and if we find a review that is the same, we mark it as a hit and we break from the innermost for loop, and we consider that as a hit. And as you can see here, yes, indeed, 1.5 is found at position 1, as you can see here, and 5 is found at position 12, as you can see here. So this is the bad way of doing it, because it's linear. It takes complexity of big O n, with n being the length of the list, which means that if the length of the list grows linearly, the time it takes for your algorithm to process and to find such an information will grow linearly as well. So it's a linear growth. But we can do better, because the length, the reviews are sorted. And in order to do that, we can use binary search. And in Python, this is done through the bisect module, which implements a function called bisect left, and there's his cousin called bisect right, but the most convenient for us, for our purpose here, is bisect left. And the way we do it is we iterate over all the list of reviews we want to search if they are in our sorted reviews, and we call the bisect left function, passing in as first argument the sorted reviews and as second argument the review we are trying to search. And bisect left will return a position, which is in fact that position is the position where that review is or should be if it's not in the sorted reviews. So to understand what that means, let's look at the result here and understand this line. So let's say we are searching for 1.5. 1.5 is indeed in the list and it's at position 1. So that's what bisect left will return. Let's say we are searching for 3.1. 3.1 is not in bisect left. It is not in sorted reviews, and if it were here, it would have been at this position, so the position just after 3.0, and this is what the position here, so the current position of 3.4 is actually the return value of bisect left, of the bisect left function. So, but since that position, at that position we don't have 3.1 but we have 3.4, this other condition will be false, and hence we will consider that it's not a hit. So that's how bisect left works, and it enables us to do binary search, which is logarithmic of log n time complexity instead of linear. And our second problem statement is, let's say not only we wanted to search for new reviews, but actually we wanted to append, to insert new reviews to the sorted list of reviews that we currently have. Well, another way, one way to do this would be, for example, to first of all append, to extend the list of currently sorted reviews. This is the list of sorted reviews, and these are the reviews that we want to insert. One way to do that will be to extend the sorted reviews with the new reviews and then perform a sort. But why is this a very bad idea? The reason why it's a bad idea lays down at this line, and the point is, sorting, the best sorting algorithm currently known to date take n log n time. So if you look at our pretty picture here, we are in this regime. Oh, actually it's not printed on this picture, n log n, but it's something here. So it's worse than logarithmic time, and it's worse than linear time. So it's a picture somewhere here like this. It goes like this. So for that reason, this is not a very efficient way to do the insertion of new reviews, because it's n log n time. It takes n log n time to do such an operation, n log n. Well, there is a better way, and the better way is to leverage still on the bisect module in Python, which also provide us a nice function called insert left, and this enables us to insert. But first, before inserting, we have to search using binary search and then shift the elements. And let's see what that means. So here, first, we are trying to insert, once again, this is our list of sorted reviews, and these are the new reviews we are trying to insert. But instead of appending to the end and then sorting, we want to use the bisect insert left function. And in order to do that, we pass as first parameter the sorted reviews, and as second parameter the new review we want to insert. And what happens is that, let's say we are trying to insert 3.4. Okay, let's say this is what we are trying to insert. Internally, what bisect insert left will do, it will iterate, like use binary search on this sorted list in order to search what is the best position where we can fit 3.4, and this is where we can actually insert that. And like we just saw earlier, such search using the bisect module, which under the hood uses the binary search algorithm, will take log n time. So we have now the position where we want to insert, but currently it turns out that something is already at that position, which is 3.9. So if we want to insert something here, we have to shift everything to the right. So we will have to put 3.1 at this position, and everything else we have to shift to the right. Hence the additional time of n, which is the time it takes to shift everything to the right. Because why is it log of n? Let's say we were trying to insert, let's say, a score of 0. The position returned by binary search will have been the position 0, and in order to insert that, we will have needed to shift everything else, all the other scores, to the right, which is the worst case complexity of big O of n. And altogether, these two can be reduced to big O of n, because this time complexity is preponderant over this time complexity. So we can just consider that the time it takes to insert is big O of n, which is still better than n log of n that we had earlier with this bad way using the sorting function. And as you can see, the insertion works pretty well. It inserts at the right position, and it is efficient. That's the end of this recipe. Hopefully you learned something new. If the case, please give it a thumbs up. Also feel free to ask any question in the comment section. I will do my best to answer those. As always, you can find the link to the code in the description below. Be sure to subscribe for future videos, and thanks for watching.